Hey guys, welcome to Mini-URT number 3. Slight deviation from the last run that we did. This time we've had a student request to look at the geomorphology of converging plate boundaries. Alright. Personally, I'm not a geologist, so I'm going to leave the hard stuff to Mary to answer. So half of this Mini-URT will be me probably introducing the more basic concepts of geomorphology and converging plates. But I think I'll leave the fore arcs and back arcs and some of the theories behind exactly how the landscapes have been formed as a consequence of subducting plates. So to begin with, thanks for the request, by the way, Mark, much appreciated. I'm not sure whether user requested tutorial is the right acronym, but we're getting there. Alright, so effectively, I'll just describe geomorphology or define it a little. Geomorphology is just the way that a landscape has been shaped as a consequence of geological processes. And some of those processes can be superficial, like hydrology, atmospheric. But you can also have much more longer timescale processes like the convergence of two plates. So two of the concepts that I'm relatively clear about, one is what's called the accretionary prism, which forms when you have two plates colliding with each other. So here is a picture of a couple of plates, and they are they're converging. One plate is subducting under the other. An accretionary prism forms by effectively the scraping of the subducting plate by the overlying plate. So you're scraping off the surface. So imagine if you've got a bit of grime on a surface and you use your fingernail to push against that surface. After a while, you end up with a lot of that material sitting on the top of your finger. Right, so this is effectively what an accretionary prism is. Right, things get tricky when the plates do all sorts of weird things, like maybe the subducting plate gets a bit heavy and breaks off, and then you end up with rebound and a whole pile of other things. I'm going to let Mary explain the more technical stuff in a bit more detail. Mary, over to you.
Other side, isn't it though?
No, it's the right. Yeah, it's that way. Yep, see,
is it that way?
That way there, you're
looking
at the green. Yep,
no, but when I'm talking to you,
at the green screen.
At
yeah,
the green screen.
Yeah,
okay.
Yeah.
Yeah, I'll be delighted to help out here. Okay, subduction zones are fascinating things. We haven't got a lot of direct observations. How do we know what happens at plate tectonic boundaries like subduction zones? And mainly, I have to admit, as a geochemist, it's through geophysics. And geophysics, seismic imaging of cross sections of subduction zones, such as this one here, they actually show us the different layers of rock, and we can differentiate between ocean crust, the mantle underneath the ocean crust, the sediments on top of the ocean crust, and we can see where they're being scraped off by the overriding tectonic plate. Now, that tectonic plate that's overriding is either going to be a continental crust on top of the plate, or it could be another oceanic plate. And basically what happens is it behaves like a bulldozer. It literally scrapes the sedimentary material off the surface of the ocean crust, and also removes some of the very altered, horribly altered basaltic material off the ocean crust. And this ends up in these things called accretionary prisms. And this one here is a stunning seismic example of an accretionary prism, because it shows you the ocean crust subducting down. You have all the accretionary prism wedge faults, and you can see the continental crust behind that. And actually at depth you can see a seamount, and we'll go into that later. Okay. So you have an accretionary prism which is accreted, i.e. wiped off sediments and stuff off the slab that's going down, the subducting slab, onto the side of the overriding slab. And this can take place in a very plastic way. So it's almost like you folding a piece of paper or a cloth. You can just rumple sediments off. It's happening quite slowly. And you end up with these wonderful foldy structures in softish sediment. But after time, with compaction and the accretionary prism growing, then you end up with these big fault structures showing. And these are these main thrust faults that you get through these things. And usually they all go down and base out on something that here is called a megasplay. Sounds fascinating. And these are big crust cutting faults. They go right down to the base of the crust. So that's accretionary prisms. If you're lucky enough to see an accretionary prism that's been exhumed, brought back up to the surface, it has the most stunning geology in it, and they're places where you get a lot of ore deposits as well. Okay? Out of interest, there are accretionary prism type structures and lots of crustal cutting faults all the way from here, cross through Kalgoorlie and to the east of Kalgoorlie, because this whole Yilgarn Craton from Perth to the east of Cal is a series of accreted terrains. They were all islands, much, much smaller than Borneo, that as subduction occurred a couple of gigayears ago, 2.4, 2.5, 2.6 gigayears ago, they all got just plastered onto the side of the continental block, and that's what the Yilgarn is. Okay. So you were wanting to know about back arc basins, and back arc basins occur usually when there is a continental plate somewhere on that overriding plate, but you may have oceanic crust as well on it, and so you have subduction occurring some distance away from so the subduction is occurring like that, the overriding plate is coming in, you always have the island arc on the side of the direction of subduction. So just by looking at a map and you see all the arcs, then you can work out which way subduction is going between the arc and the trench. They're always the other side of the trench from the subducting plate. And then behind those arcs, you can sometimes get a minor amount of seafloor spreading going on. And that's because at the subduction zone, yes, you have the accretionary prism forming, but you also have a little bit of, it's called rollback almost. It's like an erosion of the nose of the plate coming the other way. So effectively, as this goes down, it's almost rolling a little bit of the plate down with it and eroding it, sort of like scraping it. And so you get a slight pull, a tensional effect on the top of that overriding plate. And if you've got a big continent over here, which means you have a big lithospheric keel, a very thickened crust dragging on the mantle, it's just like a racing yacht, then that means that doesn't want to move this way quickly, and so consequently that's anchored. You're pulling here, and you end up with the crust thinning and being stretched and being torn apart, basically, just like a mid-ocean ridge starts. And you will actually get some ocean crust, some basalt being erupted, and a small version of a mid-ocean ridge, but it isn't. And they rarely go to full spreading. They usually spread a little bit and then stop, okay, because arcs are very ephemeral features. The nice thing about the original diagram I showed you was, as I say, there was a little seamount at the bottom there. And you can see that there is a change in slope from the subducting slab going across to the seamount, and the angle shallows out of the seamount. And this is because we have often thought of the fact that seamounts act like hairballs in drains, okay? They jam the system up, So if you think a seamount is a volcanic eruption, an off-axis eruption, so it's happening through ocean crust, it's not occurring at the mid-ocean ridge usually, and it's a volcano that's a couple of kilometres high, and of course will go down, there'll be thickened crust underneath it to balance it, so the whole thing's isostatic equilibrium. And that when that approaches a trench, then you can imagine that it doesn't actually go down and through and into the mantle as easily as the rest of the ocean crust. And it causes a point focus for the pressure regime that you're in there. And you often get little tears each side of that. These are transform faults. And then the rest of the plate will subduct either side of this wedged volcano. And you'll actually get the material behind the volcano ruttling up and forming these little folds, and then sometimes that will shear and pop up. It's an isostatic rebound that you get. And then it wouldn't be a big leap of the imagination to think that that may actually start to go over what we're thinking of as the overriding plate. Okay, so you can actually have a plate boundary that is subducting mainly in one direction, but you've got faults coming up it, and part of it is going up and over. So you've got both directions of subduction. You've got subduction and abduction, i.e. up onto that crust. And that could be one way that you do form fossil ocean crusts that we find, ophiolites we call them. I went over in the lecture.
Cool.
I think we could go on forever, but we won't. But I think that isn't 100%. Nobody really knows. But the seismic data that we have and the isotopic data and the chemical data that we have all seem to agree that this is the way things are going. The work that's been done in the Yilgarn, you can actually work out which was the first. The terrains as you go east are the oldest. So the most easterly terrains are the oldest, and each terrain boundary you cross, which is one of these major splay faults, you drop about 100 million years or something like that. And so it looks as if we've accreted about 6 quite largish, but not, as I say, as big as Borneo islands, and they've all just been plastered sequentially on next to each other. And that's what's formed the goldfields. And you can see those crystal cutting faults if you have a look at a geological map. So we have a perfect example here of a fossil one 2,000 million years ago, just over 2,500 million years ago. And we can see the same thing happening in the ocean to the north of Australia.
Cool.
I take it you're happy with that, Andy?